This video discusses thermal analysis of a circuit in Microwave Office, where the RF input signal is not just a continuous sine wave of constant frequency and amplitude, but is instead modulated. This class of stimulus is referred to as an envelope signal. The particular case discussed here is a pulsed RF waveform. Microwave Office uses as its thermal simulation engine Cadence's Celsius simulator. Celsius is fully integrated with Microwave Office. There is no manual transfer of data between Microwave Office and Celsius. It all happens behind the scenes. This example uses a simple Gallium Nitride or GaN power amplifier mimic, composed of 4 GaN HEMTs, where the gates are connected via a pair of successive 2-to-1 splitters at the input, with the same geometry in reverse acting as a combiner for the drain outputs. The devices are all biased in class AB. There's the bias point. This graph, P in versus and P out, shows the results of a conventional harmonic balance analysis for a continuous 1 GHz sine wave stimulus. Plotted are power out, power gain, and power added efficiency as a function of the input power. For analysis of the pulsed RF signal, the PA schematic is embedded in a test bench where the stimulus signal is an RF pulse of frequency 1 GHz, duration 50 microseconds with 15 dBm of available input power. Before thermal simulation can be performed, data must be generated as input. First, a harmonic balance envelope simulation is performed that, as well as calculating the output power delivered to the load over time, also calculates the power dissipated by the amplifier throughout the period of analysis. This is shown for the entire amplifier. A measurement in the group output files generates a granular data file of this information, showing the power dissipated in all schematic elements of the amplifier as a function of time. This is used in the thermal analysis. Also required is a 3D geometry defining the physical structure, including definition of the locations where power is dissipated. In this case, in the vicinity of the gate finger of the transistors, highlighted here in red. To generate this 3D geometry, we need to define the physical materials associated with the shapes created in the circuit layout. This is done in the stack-up, specifically in its layer mapping section. In Microwave Office, we can automatically create the 3D geometry from the circuit layout using a process known as extraction. This utilizes the same Microwave Office framework used to generate geometries for EM simulation. The final pieces of the puzzle are: 1. The thermal properties of the structure's materials, which are defined in a file as shown and referenced by the stack-up. 2. The backplane temperature, which is defined in the structure's properties. We are now ready to perform the thermal simulation. When we initiate that simulation, the various input data are passed to Celsius. The structure is then meshed using automatic mesh refinement to create small mesh elements when necessary, the heat equation solved, and the data passed back to Microwave Office for display and analysis. A results window is automatically generated that displays the maximum, peak, and average temperatures for each heat generating volume over the period of analysis. These can be examined individually. The user can also generate a plot of temperature as a function of time for any heat generating volume. Here is a graph showing the peak and average temperature of an individual FET finger over the course of the 100 microsecond simulation. As one might expect, the temperature climbs during the period of the pulse. it has not yet reached an equilibrium by the time the 50 microsecond pulse finishes, at which point it starts to decline. The user can also add a visual notation to the 3D structure simulated, showing the temperature variation across the geometry. Here we pick a time value, 50 microseconds, i.e. toward the end of the pulse. The initial view is somewhat obscured by the simulation mesh and the passivation layer over the amplifier HEMTs. By turning these off, we get a clearer view of the fingers. We can add a cut plane to see the heat penetration in more detail. Note that this example simulates only a single pulse and assumes that the entire structure is at room temperature until the simulation has started. You can see this in the graph of FET finger temperature versus time. At the end of the 100 microsecond simulation time, the temperature is still declining. In a more real-world scenario, we would expect that the transistor would be stimulated by a pulse train and therefore would reach an average temperature elevated above ambient. AWR Celsius does have the capability to use a previous simulation result as the baseline. For a pulsed signal, the structure should be first simulated using a continuous drive signal with power equal to the average signal power of the pulse signal. The resultant dataset can be used as the baseline for the envelope simulation. This concludes this video on thermal analysis of circuits in Microwave Office using the Celsius simulation engine. Thank you for watching.